Hi everyone. In this video, you will discover what limits are and why they are useful. Let's start with an exercise. What is the end number of each of the following sequences of numbers? If you would like to try this exercise on your own first, you can download these notes using the link in the video description. I believe that the first sequence gets closer and closer to 0. The terms of this sequence, 1/2, 1/4, 1/8, and so on, they get smaller and smaller, approaching 0. The second sequence gets closer and closer to 1. The third sequence gets closer and closer to 20. Note that I put quotation marks around the word end. That is because these sequences don't actually have an end number. By the end number, I mean the value to which the terms in the sequence get closer and closer to. That value is called the limit of the sequence. So for example, 20 is the limit of the third sequence because the terms of this sequence get closer and closer to 20. Even though none of these three sequences actually reach their limits, the limits themselves can have real-life meanings and real-life applications. Let me give you two examples, one in the context of rate of change and another one in the context of area, where a limit has a real-life meaning and a real-life application. Imagine you are a car engineer. This is you. You test car crashes. What you want to do is to crash this car into the wall. What you do is you place a dummy inside of the car, you place the dummy's foot on the accelerator, and you let the dummy drive the car into the wall. What you're interested in is how fast the car was driving while hitting the wall. Unfortunately, you cannot sit right next to the dummy to look at the speedometer at the time of the crash, because then you would crash together with the car. Instead, you record everything using your camera. And after reviewing the footage, you realize that the car was about 100 meters away from the wall. You also realize that the time it took the car to hit the wall was about 10 seconds. This allows you to compute the average velocity of the car during the first 10 seconds of the trip. You take the total distance and divide it by the total time. 100 divided by 10 is 10. So, during the first 10 seconds, the car was going 10 meters per second. Unfortunately, at the beginning, the car was going slow. Later on, the car was going faster. So computing average velocity during the first 10 seconds is not the best approximation of the car's speed while it was hitting the wall. So instead, you review the footage again and you take a look what happened during the last 5 seconds, only when the car was going fast. So I did some mock computations for you, and I said that during the last 5 seconds, the average speed of the car was 15 meters per second. And you did the same thing for 3 seconds, 1 second, and the last 0.1 second. And you got 17 meters per second, 19 meters per second, and 19.9 meters per second. I believe you have seen this sequence before. These numbers seem to get closer and closer to 20 meters per second. As the length of the time intervals gets shorter and shorter, the average speed of the car gets closer and closer to 20, which suggests that the car hit the wall at the speed of 20 meters per second. If you want to know how much that is in miles per hour, 20 meters per second is roughly 45 miles per hour, and 10 meters per second is roughly 22 miles per hour. Let me give you an example in the area setting. Take a circle. A circle has a center and a radius. Let's consider a circle of radius 1. What is the area of this circle? Imagine you don't know the formula for the area of the circle. How would you compute the area? Let me show you a method that was very popular among ancient Greek people, especially in the 4th century BC. Archimedes was a big fan of this method called the method of exhaustion. Archimedes suggested that instead of computing the area of a circle, you should compute the area of a square that contains the circle. This square has area of 4. That is because one of its sides has the length of 2 radii, and squares have 2 sides that are of the same length, or all the sides of the square are of the same length. So the area of this square is 4. This suggests that the area of a circle must be less than 4. Unfortunately, 4 is not a good approximation of the area of a circle. This square contains lots of extra area. What you could do to improve this approximation, you could cut off the corners of this square. If you do it just right, you will obtain a figure with 8 sides called an octagon. That octagon will still contain the circle fully. What's more, each octagon consists of triangles. Here is one such triangle, here is another such triangle, here's another such triangle, and so on. And you can compute areas of triangles. I did it for you, and I added the areas of all those triangles, and I got that the area of that octagon was approximately 3.31. This means that the area of the circle must be less than 3.31. You could continue cutting off the corners and obtaining better and better approximations. I did that for you. When we used an approximating figure with 4 sides, we got the area of the approximating figure was 4. When we use an octagon, the area was approximately 3.31. I used a figure with 16 sides, and I got approximately 3.18. I used a figure with 32 sides, and I got the area of approximately 3.15. I used a figure with 64 sides, and I got approximately 3.14. Again, you created a sequence, and that sequence appears to get closer and closer to the value of pi, which suggests that the area of the circle is pi. So in these two cases, a limit of a sequence had a real-life meaning. 20 meant that the car drove into the wall at the speed of 20 meters per second. Pi means that the area of a circle is pi. Now, instead of thinking about these numbers as limits of sequences, I want you to first think about this table as a function. In the first column, you have inputs of your function. In the second column, you have outputs of your function. Now, as inputs of your function get closer and closer to 0, the outputs of your function get closer and closer to 20. In the second table, as the inputs go further and you have more and more number of sides gets larger and larger, the inputs go to infinity, the area, the outputs, seem to get closer and closer to pi. That number to which the outputs get closer and closer to, as the inputs get closer and closer to some other value or infinity, is called a limit of a function. So intuitively, the limit of a function is the value that the function gets closer and closer to as the inputs get closer to a given number or infinity. In the first example, inputs were getting closer to 0, the outputs were getting closer to 20. In the second example, the inputs were getting closer to infinity, the outputs were getting closer and closer to pi. That value to which the outputs get closer and closer to is called the limit of this function at a particular point.